Hello everybody, welcome to Advanced Physics from Mr. O'Hagan's living room. I hope you're all doing very good out there. First unit we're going to be tackling is mechanical waves. Mechanical waves piggyback nicely off of simple harmonic motion, and you'll see why as we get into them. What we're going to be studying, first of all, is what waves are. That's first. After that, we're going to go and look at some of the characteristics of waves. Then there are a couple different types of mechanical waves. Then we're going to see graphing of waves, and last we're going to finish up with the speed of waves. All right, so to start off with, waves are things that oscillate, first of all, and then secondly, and almost more importantly, waves allow us to transmit energy from one spot to another. But you got to be careful. You transmit energy with a wave without actually moving mass from one spot to another. Let's take a look at some waves.
What we're going to attempt to do now is we are going to use this giant demonstration slinky to attempt to get energy from where I'm at to the center of the slinky. Helping me today are my boy Finn and my daughter Ailish. We will be using a wave to get energy from me to the center of the slinky. Okay, and away we go.
Please, no! 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 No!
Okay, so what happened in that clip was, although we moved some energy, we moved a whole lot of mass. And trust me, there's energy in that gallon of gasoline. So now let's try and see a wave for real.
Do it for real. By the way, I forgot to introduce my assistant, Ailish. And Finn was the wise guy with the gasoline before. Okay, here it goes. As you can plainly see, the red flag is moving. It had no kinetic energy before, and now it does.
All right, let's take a look at a couple other waves. Keep in mind, waves transmit energy, but they don't transmit mass. It means they take energy from one spot to another. Mass can move, things can jiggle around, but the mass at the starting point never makes it to the end point. The mass basically just oscillates back and forth, but never really goes where the energy goes. All right, so here we are outside. I got a rubber ducky in some water. Notice it is not moving. Here's what we're going to do. I'm not going to send any mass towards the duck. We're just going to give some waves. And now the duck is doing a little dance. It definitely has a whole lot more kinetic energy. As you can see, I've paused the animation of the wave. We've done that so we can look at some of the things, some of the properties of the wave, and some of the things that you can measure from a wave. So first we're going to start off by talking about that yellow line that goes right through the center line of the wave. It's basically the center line of the wave, huh? If we were to measure from that up to the highest point that the wave gets away from the center line, in either direction, doesn't matter, measuring from that center line, the yellow dashed line, up to that highest point, that is called the amplitude. Imagine that. The variable that we're going to be using for amplitude when it comes time to do some equations is merely just capital A. Okay, in the other direction, the direction that the wave is moving, if you measure from the high point of a wave to the high point of a wave, Or you could possibly measure from the low point of a wave to the low point of a wave. It doesn't really matter. As long as you measure from one spot on the wave to the very same spot on the next wave, I'm going to choose where it's cutting across the center line. And notice I have an entire wave there, both down and up. Okay, that distance is called the wavelength. And the algebraic symbol for the wavelength is kind of a weird one. It's a lambda, and it looks like an upside down Y. At this point, we've only ever talked about one type of wave. There's really two types of wave, and it depends upon which way whatever's moving is moving. So for example, with the giant slinky, it's which way the coils are moving. One of the types of waves is called a transverse wave. That's what we've been seeing the whole time. The other's a longitudinal. I got two video clips which will help explain the difference between the two.
Okay, the first type of wave we're going to have is what's called a transverse wave. When the slinky moves, the coils are going to move at a right angle or perpendicular to the direction of the wave. The second type of wave is called a longitudinal wave. The motion of the coils will be in the same direction as the wave is moving.
It's now time to talk about how to graph waves. For graphing, I think we're going to start off with the transverse wave. It's the easiest wave to visualize and understand. So I got a snapshot of the transverse wave. I'm sorry, I know it's difficult to see a gray spring on a gray background. But anyway, it's there. What we're going to do is we're going to add data points to the spring so you can see what's happening. Sorry, the data points wouldn't add, but there they are. Okay, so now I have the data points on the screen. On top of the data points, let's put a curve. There's the curve. Can you kind of see a little sine wave action going there? All right, once we get to this point, we're going to put the center line and the vertical axis for our graph, because the whole point of this is we're going to be graphing. Now, let's take away the spring and leave just the graph. There it is. Next, we're going to take away the data points. And you understand, you see in our graph, the problem is we're zoomed in really close to our graph, so we can't really see the sine waves. So I'm going to take the x-axis, the horizontal axis, and I'm going to shrink it so I can see a lot more of the wave. And when I do so, there it is. Beautiful wave pattern. And just think, that's that spring bouncing back and forth and back and forth and back and forth across the ground. All right, my two axes. Of course, this came from a picture. So the two axes have to both be position. The x-axis is position, the y-axis is position. And that's how you graph a longitudinal wave. X-axis position, y-axis position. It makes plenty of sense. It's like taking a picture, just like we did. Okay, now let's do the longitudinal wave, because this one ends up causing a little bit of trouble. So here's my my snapshot of the spring. I know it's not easy to see, but it's there. Actually, the shadow is easier to see than the spring itself. I'm going to add data points to this, and that's going to be trouble. Okay, let's add the line for the graph, and it's just horizontal. That's no good. Okay, what about the axes? Here are the axes, and if you look, if you understand what's going on, we get absolutely no information from this graph at all. None whatsoever. All along the x-axis, we just have zero displacement. Well, that's kind of miserable. All right, so if I try and plot this position like I did with the transverse graph, again, I get no data, no information. That's trouble. So what we're going to do is we're going to peel off the data points, we're going to peel off the line, and we're going to peel off the label on the y-axis. So now we're just left with the x and y-axis. We know x is going to be position, y-axis we're not sure about, and we have the spring there. We're going to put the data points back on, but this time, instead of making them equally spaced in the x-axis, we're going to space them according to how bunched up or spread apart the coils of our slinky are. So in the middle, as you can see, the coils are pretty bunched up. They're close together. There's a high density of coils. And then as you get further away from the center, you get quite a bit less the coils. They're spread apart. There's less of them per meter, let's say. So if we have this, now this lends itself to making the y-axis density, because we just put in dots which represent what the density are. High density areas we're going to make above the line, low density areas we're going to make below the line. And that's what it looks like. And now take away the data points, take away the spring, and you're left with a graph of a longitudinal wave. Longitudinal wave, the x-axis will be position, just like in the transverse wave, but the y-axis has to be density. And the density can be whatever you need. In this case, it would have been coils per meter. If it's sound would be pressure. The density would actually be pressure. How many molecules there are per meter or whatever, per cubic meter, I guess it is. Anyway, that's how you graph longitudinal and transverse waves. Today's lesson was made possible through ongoing support from students like you and the great outdoors. I bet you thought we were done graphing, but we're not. The graphs we've done up till now have position on their x-axis. And if position is on their x-axis, there's nothing to do with time. And so basically you're getting a snapshot of your wave at some instant in time. Well, we want to know what's happening to the wave as time goes on, or what's happening to at least a part of the wave as time goes on. So we're going to start this here animation. And we're going to start tracking the very center green ball as time goes on. In order to do that, we need to get a couple things. We're going to make a graph. That's what we're going to do. So we need to get a couple things. Let's get the ruler set up. So with this ruler, I can figure out what is the amplitude of this green object as it goes through its oscillations. Okay, so let's see. I got it so at the very bottom it's 0, at the top it's 2. Oh, guess what? That means that's the total swing. The amplitude has to be half of that from the center line out, so the amplitude is 1 centimeter. Yay! All right, we got the amplitude. Now we have to figure out how much time it takes for this to repeat. Because remember, we're going to take this green dot, which is going up and down, the one in the middle, and we're going to track what's happening to it as time passes. So we know the pattern keeps repeating. Let's figure out how much time it takes for it to repeat. Okay. So what we're going to do is, oh, there's a timer. How fantastic is that? So let's set the timer up here to make our lives a little easy. And I'm going to time this from the time it's at the top until it gets back to the top. But I'm going to do it for 2 or 3 cycles. Now let's make it 2 cycles. 2 oscillations. It'll cut out some of the error. Okay, and here we go. And start. And that's 1. And stop. Okay. 3.98 seconds. Divide that in half, 1.96. Guess what? I'm going to call that 2 seconds. This pattern repeats every 2 seconds. So let's recap. We're going to make a graph, a position time graph, which has an amplitude of 1, and it has a period or amount of time that it takes the oscillation to repeat of 2 seconds. All right, we're going to do that in just a moment. Okay, we've taken all the information about our graph, what's happening to that center green point as time goes by. We know we had an amplitude of 1 centimeter, that's 0.01 meter, and we had the time for one wave to go by. Oh, look at that, I spelled it wrong. Anyway, time for one wave to go by is 2 seconds. By the way, that's called the period. So I've set up my axes, time in the X, position in the Y, and I got things, okay, I got my numbers up there pretty good. We know that green ball was at the very top of its path when we started the timer. So my first data point at time equals 0 is going to be at 0.1. We also know that it took 2 seconds for the whole thing to repeat. So at 2 seconds, we are going to be back again at 0.1. There's my first 2 points. So let's see, 2 seconds for one whole oscillations. After 1 second, it would have been all the way at the bottom. There's my third point. Half a second, it's going to be at the midway points. So there's my next 2 points. And I know the patterns are going to repeat, so I can just fill in everything else. All right, that's kind of easy. Okay, let's put a line to it. And there we go. That's how you graph a transverse wave in what's called the time domain. We are tracking what's happening to that center green ball as time ticks on. Versus, if the x-axis was position, we would be looking at the entire wave, but only at one instant in time. One last comment to make. The distance between these 2 points, basically between any same 2 points on 2 successive waves. All right. The last time we measured this was the wavelength, except we know it can't be the wavelength now because our x-axis is time. So what this is, hey, I think you might have guessed it. This is the period. Because we knew it was the 2 seconds, and of course, we've just measured from 2 to 4. That's 2 seconds. Yay, we have finally come to the end of making graphs. Next up, we have to interpret graphs. Okay, everybody, let's wrap this up by doing a couple sample problems. The thing to remember for both these sample problems is I'm going to give you 2 graphs. Both the graphs represent the same wave. If you look at them, graph on the left is going to have position on its x-axis. The graph on the right is going to have time on the x-axis. Same graph, but just pulling out 2 different bits of information. The one on the left, what we're seeing is a snapshot of what the entire wave is doing at one moment in time. On the right, we're seeing a graph of one location on the wave and what it's doing as time goes on. All right, so without further ado, here we go. Looking at these 2 graphs, the y-axis is position in both of them, so we know it's a transverse graph. So I'm going to write that down. Okay, looking at the graph on the left, actually looking at both graphs, the amplitude is 1 meter. So let's write that down. Okay, looking now on the left graph, the one that is a position, I can get the wavelength, how far it is, the length of one wave. So let's see, I have to get, so here's the start of a wave, here's the end of the wave, that's 0.2 meters, I'll write that down, wavelength 0.2, all right. And now from the graph on the right, what I can get is the period, how long it takes for one wave to go by. So, period's going to be half a second, so I'll write that down. Okay, at this point, this would have been all the things we would know how to do reading from a graph. But there's one more thing. Because we know both the wavelength and the period, how long a how long a wave is and how much time it takes one wave to go by, we can figure out how fast it is. The equation for the speed of a wave is wavelength equals, oh, no it's not. The equation for the velocity of a wave is velocity equals wavelength divided by period. So I got that one written down. And let's just pull some numbers out of the information that we've taken. So that's going to equal wavelength 0.2, and on the bottom you got 0.5, and 0.2 divided by 0.5, oh, it's like multiplying by 2. So it's 0.4 meters per second. That's how fast this wave is going. I decided to only do one sample problem after all. I hope you've enjoyed this lesson. Until next time, this has been Mr. O'Hagan.